So
Specific.
like we had bounded it by n-1, but like something is less than n-1. I actually forgot whether
This
it
one,
was kappa or lambda.
this one.
Yes. Yes. So like when we remove n-1 vertices,
Hmm?
then it's still vacuously connected, right?
Yeah. So
The
we usually say that connectivity is at most immense in the sense that once you isolate one vertex, right? It is true. What you're saying is when there is only one vertex. So we are assuming that the graphs are simple, right? So there is no path from this vertex to this vertex unless there is a loop. Yeah. So
yes.
we don't say that like if just one vertex remains, then we are going to say that at that point the graph becomes disconnected.
Okay.
Okay. So
Okay.
in that, if you want the graph to be still connected, it intuitively means that there should be a loop, and we are only looking at simple graphs.
Yeah.
Yeah, it's a bit uncomfortable in the sense that there's only one vertex, so vacuously the graph is connected. Right? What you said is right. But we will look at it as there's this one vertex, but there is no path from it to itself.
Um, yes, ma'am. Because like the doubt arose because even in general, when we define connectedness or something,
Connectivity.
yeah, connectivity, we say that like between any two distant vertices, there should be a path, right?
Right. 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 That's true. That's true. Yeah. So that is why even in the case of complete graphs, it's said to be at most n-1. Yeah, I understand that it's a bit uncomfortable. This one, right? Yeah, you would expect like yeah, you wouldn't say the graph is disconnected when there's one vertex. Yeah, but that's what the terminology is.
Okay.
When there's just one vertex, because we're looking at simple graphs, we say that at that point you have disconnected.
Okay, ma'am.
Are there any other questions? Yeah, please ask questions. Okay, so if there are no more questions, let's look at graph color. So today we will look at graph coloring and also some. Yeah, did someone ask a question? Graph coloring and planarity in graphs. But let's just continue with graph. So a legal coloring or a proper coloring is whenever you're given a graph, you have to assign colors to vertices such that if you look at any edge, the two corresponding vertices, right, they should get different colors, or adjacent vertices get different colors. They should not get the same color. Such a coloring is called a proper coloring in a graph, and this is denoted by chi. Yes, I understand that there are a lot of terminologies here. Like we used kappa of G. So we have kappa of G, which denotes vertex connectivity, and then there is lambda of G, which denotes edge connectivity, and we have chi of G, which denotes the chromatic number. And there are more things we will see today. So chi of G is the minimum number of colors that you need to proper color a graph. So you're given a graph, that's the minimum number of colors that you need in order to ensure that the adjacent vertices get different colors. So trivially, you know that chi of G is at most 10. So if you give all the vertices different colors in the graph, definitely all the adjacent vertices will also get different colors. And you need at least one color. So you know that chi of G is at least one and at most 10. And we also saw that if a graph is two colorable, so when we say k colorable, we mean that there is an assignment, there is a proper coloring of G where you use at most k colors to the vertices. So the first upper and lower bound is this. Right? So chi of G is at least one and at most 10. And we also saw that if a graph is two colorable, then it is bipartite, and any bipartite graph can be proper colored with two colors. Similarly, that's the case with complete graph. So these two are just some examples. Okay. So now we want to understand chromatic number better. Just like we saw vertex connectivity, edge connectivity, and then we found upper and lower bounds of this. Now we are going to do the same thing for chromatic number. So let's try to understand. So now let's just think about it this way. Suppose you are given a graph G, and there is a vertex B which has, let's say, D adjacent neighbors. That is, this has degree D. Degree of B is degree of B is D. So there are neighbors V1, V2, V3, so on to V2. So you know that there is a vertex B that has degree D in the graph. If that is the case, then what can you say about chi of G? There is a vertex B here that has degree, exactly D neighbors. Is the question clear? It's not at all a difficult question. Let's just try to answer. I'm not
At
sure.
least
So,
D
so
plus
it,
at least D plus one.
okay, right. So let's give this person a red color and then keep giving colors like this. This one blue, the next one green, and so on. Because this vertex sits inside the graph, if you want to proper color the graph, all the neighbors, right, all of these should get distinct colors. Colors that are different from, when I mean distinct colors, colors that are different from the color red. Right? So then you will need at least D plus one colors. Is this clear? So the first bound that we have,
Ma'am, what if like the other V1 up to VD are not connected? Then can't we color all of them the same? Like
right, right.
suppose
Okay. Yeah. So I'll understand as usual. So what is the inequality? Yeah, that's right. Actually, that's right. So it would be at least, or what can you say? Right. So if so, okay. So what is have to define that? Okay, so let me not write it this way. So let us say that the maximum degree of any vertex in G is D. So then what can you say about chi of G?
it should be at most
Yeah, yeah. Okay, so to trouble you more, this maximum degree is actually called delta of G. Okay, but yeah, let's not. So for those of you who read a textbook and you see delta of G, you should know that this is the maximum degree. So that is why I'm saying that you don't have to remember these things. Generally, G is written as at most delta of G plus 1. Okay. So even to prove this, it's not very difficult. What you can do is, so what are we trying to say? So we are considering that G is a simple graph with max degree delta. Then G is delta plus 1 color. So you can actually prove this inductively. So you pick the vertex of the largest degree, you remove it from the graph. Any graph has axis. The largest degree is delta, so the remaining graph is a delta plus color. Now you can put B in, it will have at most delta neighbors. Right? So there is one remaining color that you can give to B. So now note there is an upper bound of a delta of G plus 1 type. So what's a lower bound on delta of G? Next question. Okay, so now for that, let me give you an example. Okay. So let's consider this. Let me add some stuff here. So now, how large, how small, how small can the chromatic number of this graph be? So color this graph with three words, with three colors.
We need at least five,
Why is that?
because we have the five vertices, all of which are connected with each other. So all of them have to be distinct colors.
Exactly. But you see this, because there is a K5 sitting inside, or a complete graph on 5 vertices sitting inside this, it is not possible to color this graph with 4 colors. Right? You at least need 5 colors for this, and then maybe you can still reuse. For example, this red, blue, green, yellow, violet. You can use violet, yellow here. Okay? So now more notation. So now if you look at any graph G, it is possible that there are complete subgraphs that sit inside this graph. Right? So what is a complete subgraph of this one? Right? What do you call it? It is called a click. So a click in G, let's say G is a simple graph. A click in G is a subset of vertices. So let's call this subset S. So it's an S subset of B, such that for all A, B in S, A, B is in the edge set of G. So in other words, it's a complete subgraph that sits inside this original graph. So this sits inside. So some graphs might have a triangle only, then the side, the click is K3, for example, this might be a graph, right? So then one might ask, what is the size of the largest click that is inside this graph? For example, here it's K3, right? And here you have a K5 sitting inside. So the size of the maximum click or the largest click G is called the click number of the graph. This is denoted by omega of G. So delta of G. See, so you don't have to remember these things. I'm writing these things here because tomorrow when you open a textbook, like these things might be defined in the first chapter and you might be reading the fifth chapter. So you might not know what these notations are. It's just for that purpose. But some things are essential. Those things it's good to click now. Okay, so now I've given you sufficient information about what the click number of a graph is. For example, click number of this graph here is 3. Click number of this graph here is 5. Okay, are there any questions about click number? If you have not understood it, we should do this. Okay, so now can somebody tell me what the chromatic number of the graph should be in terms of the click number?
It should be at least equal to the chi of G should be at least click number of G.
Right. So can everybody see this? So chi of G should be at least omega of G. Right? If you're able to do with lesser than omega of G many colors, that means that there is an edge in the original graph. Both of these endpoints are the same color, right? Because there's a click of that size in the graph. Clear to everybody? Otherwise, we can go with this. Okay, so now we have two inequalities. Chi of G is at least. Right. So now I want to actually just state a theorem, but we want to prove this. It's called Brooks theorem. It's actually a very nice theorem, just that it's a case analysis. So we have to sit patiently and do all the cases. So we are not going to do it, but I will give you the statement. So we said that chi of G is at most delta of G plus 1. Right? So if there is a vertex in maximum degree, then you have to you can color the vertex with delta of G plus 1 many colors. It's a trivial thing because the maximum degree itself is delta of G. How large? I mean, you could do it with plus 1 colors. So Brooks theorem actually tells us that you can do better. You can just do with delta of G many colors itself. You don't need that plus 1. It's actually a very interesting statement because what it means is, see, even though the maximum degree might be B, now if you look at B and its neighbors, you will need like delta of G plus 1 many colors. That's what it is, right? Otherwise, if you're able to do this with delta of G plus 1 many colors itself, delta of G many colors itself, you should somewhere go wrong. But actually, Brooks theorem tells us that that's not the case. So you can do some color adjustment. and somehow get it to delta of G itself. So we will not prove this in class. It's a bit, yeah, it's not difficult to prove this. Okay. It's just that it's very painful to sit and write those cases. So I will just write down the key. So let's say that G is a simple connected graph. Just okay, so does anybody see a problem if I make this chi of G to be delta of G right away? Is there some graph for which this won't be a good one? So maybe I will write it and then we'll see.
Ma'am, I actually have a doubt in the induction argument for that. So you said if we remove the vertex with maximum degree, then the rest of the graph will have maximum degree delta minus 1. Is that
Correct.
what you'd say? But
Yes.
what if it does not? Like, what if there are two vertices that have maximum? Okay, it will.
So it's an induction on the number of vertices.
Okay.
So you delete a vertex, you delete the vertex and all its incident edges, right? So the remaining graph is a graph with n minus 1 vertices and the maximum degree is still at most delta.
Right. So that would be delta plus 1 colorable. And now, right. So there are only, yes, ma'am, I get it.
But B has at most delta numbers, right? Yes. So only delta colors you would have used from that list. If you like write down red, violet, yellow, then only delta colors you would have used. One color will be red.
Yes, ma'am.
Now the difficult portion is in Brooks theorem, you cannot even use that one color. So you should use already used delta colors, right? Then it seems very non-trivial, right? So to do some color adjustment, so some people call this color refinement. So you first start with some coloring and then slowly adjust the coloring so that you are going to reuse as many colors as possible. So which is not a complete graph. Then, and let's also assume that the maximum degree is at least 3. G is delta color. So this proof is also by induction, but it's slightly non-trivial in the sense that so let's just look at it. Suppose you have like a vertex B and it has delta neighbors, right? B1, B2, so on to B delta. And you give each of them a different color, C1, C2, so on to C delta. So you have Bi here, you have Bj here. This gets Ci, this gets Cj. And what we want to sort of argue is you look at the connected components here, look at the connected components here, and try to adjust the color so that these two get the same color, like Ci, Ci. But whatever is connected to this, you still ensure that, so you begin with the coloring and then you say that, okay, whatever remains here is all proper coloring. And I change the colors slowly so that both of these get the same color. So that I'm free to use one color, one of these colors, right? When both Ci and Cj become Ci, Cj is free. So you can use that for B. So that is the idea, but it's a proof by induction. Okay. And the number of vertices. But we will not do this. We are not doing this because it's painful to look at all the cases. I mean, look at the connected components and see how to adjust the colors. But it's a very nice exercise, a challenging exercise if you want to take it. So it's good to know that it's not just delta plus 1, it's actually delta. You can do much better. Just looking at the maximum. Okay, so is this clear? Like so far, whatever story just happened. Okay, if it is, then we will move to planarity and come back to color. We will actually come back to color in a while, but let's just talk about planarities. Okay. So now let's look at K4. It's this graph. And there are applications where you don't want these edges to cross. Okay? For example, if you look at road networks, or let's say you want to build like flyovers, then you don't want these to cross, right? For example, one of them is a flyover and the other, let's say, is the underlying road. Or this could be even in the case of integrated circuits where you don't want too many wires to cross to cause interference. So in these applications, you don't want edges to cross. And these applications are usually modeled by graphs where there are no edge crossings. So the question is, can you draw this graph on the plane without edge crossings? So do you think that you can do this?
Yes, ma'am.
So let's try to do it this way. So this is a drawing of the graph. So it's the same graph. You should be able to observe that it's the same graph. The only difference is that between this graph and the graph is the way you have drawn. There are no edge crossings in the first graph, whereas there is an edge crossing in the second graph. So a graph is planar if, say, so graph G is planar if G can be drawn on the plane without edge crossings. Okay. And such a drawing is called a plane representation. Is the definition clear? So a planar graph is a graph that can be drawn on the plane without edge crossings. So this must hint you that possibly there are graphs for which you cannot do this trick. So K1 is just one vertex. You can draw it on the plane without edge crossings. There are no edges. Next is K2. Then you have K3. Then there is K4. So K5, let me just draw it here. There's not much space. So can someone draw this graph on the plane without edge crossings? Let us just try to do that. Okay? So, somebody wanted to answer? Yeah. Okay. So was there a question?
No, ma'am. I said we can't do the same thing as we did with K4 because K5 is not played.
Okay, so let's try to formally see why you can or cannot do that. So this pentagon I can safely draw on the plane. Now I have to add 5 more edges, right? So let's add some edges. 2, 3, 2, 4. So now I have 2 more edges to add. Okay? One is 1, 4, and the other is 3, 5. Now 3, 5.
And also 1, 3.
Yeah, there was a question from there.
There are 3 edges to add, not 2. That's all.
Sorry.
And we also have to add 1, 3 edges.
Oh yes, yeah. We have to add this one. These two have to add. Okay, so 1, 3. I think this is fine. So far it's okay, right? Seems okay. Yeah, please tell me if there are mistakes. Okay, so this edge remains. Now there are 2 ways to draw this edge. One is inside the pentagon. The other is outside the pentagon. If I draw inside the pentagon, I will cross 2, 5. If I try to draw it outside the pentagon, I will cross 3, 5. So this graph is so when I mean by non-planar, what I did was I just tried to draw this because it was a small graph, and it might still seem that you are not very convinced, right? Why you have to draw the graph. So we have to formally prove why K5 is not planar, but this should give you an intuitive feeling. Okay, so either the edge should go inside the pentagon or outside the pentagon. In any case, it will cross an edge. Right? So this is the first complete graph that we have seen that is not planned. Let's look at some more graphs. Let's look at K12. So are you familiar with this notation? I'm not sure if you introduced it. So this is the complete bipartite graph on like one partition has one vertex, the other partition has two vertices. This is planar. So K1n is planar for any n. Let's look at K22. That's this graph. Is this planar? Okay, I should put one. Is this graph planar?
Yes, ma'am. You can draw a square for that.
Right. It's just a cycle, right, of length 4. So now let's look at. Similarly, you can look at K23. So this also you will see that it's a cycle of length 6. Okay. So now K3. I'm going to draw this for you and you will have to tell me whether it's planar or not. So is this graph planar? So there is an underlying 6 cycle. So let's just draw that first. Just drawing something and hope it's right. Let's see. And then 2, 3 at the draw. 4, 6 is there. Now what is the edge that remains?
1, 5.
This I missed something.
No.
I think I missed 2, 5. Okay. I've drawn 3, 4. I've drawn.
Also 1, 3.
Yeah, sure. So one edge remains is 3, 6. So yeah, as you see, 3, 6,
1,
8.
6 also remains.
Thanks. So now only 3, 6 remains. I hope. Yeah, I didn't count edges. But at least the idea is now to draw this edge, you have to either go inside the hexagon or outside the hexagon. Yeah. Okay. So if you try to do it this way, then you will cross this edge. If you try to do it this way, then you cross.
Mom, can't just stay inside the 4-6 wala edge and draw it? Meaning, we don't have to cross that edge, right? The 4-6 edge to join 3 and 6.
So I didn't get what you said. So I want to join 3 and 6, right? This is what I want to do. How
Yes.
do you want me to do? Go this way?
Yes.
Okay. Yeah. So then I'm sure there'll be one more edge. Let's see. 3, 9 edges are there, right? 3, 6, 9. Let's see.
No, 1, 5.
Yeah. That's it. So let's do what you said. 3, 6. It's fine, actually, I think. Good. So then let's look at 1, 5. 1, 5 you should do balanced. I don't think there is any way to do it either this way or you should do this way or you have to do this way. Yeah, you can try play around with it. But this is the first complete bipartite graph that's not planned.
Ma'am, I don't understand your numbering here.
Don't understand? Huh.
Like, are the same vertices represented by the same numbers in both graphs?
Yes. Did I mess up something? There is an edge between 1, 3. It should not be.
And there's an edge between 2 and 6.
Okay, messed up. Let's see. So 1, 2 is there, 1, 4 is there, and 1, 6 is there. That's fine. There is 2, 3. There is 2, 5. So that's also fine. And then for 3, there is 3, 2, 3, 4, 3, 6. Okay, and 5, there is 5, 2. There should not be 5, 3. 2, 5, 4. Okay, so there should be an edge here. 5, 4, 5, 6. Yes, yes. So the intention is you have the same number so that you can see what cycles are there, what edges are there. Yeah, so here to draw 5, 4, you have to go inside or you need to go outside. In any case, you have to cross. Yeah, you can try whatever they suggested. This way, this way. Yeah. So it won't work. And K33 is non. So when I say that, it's a bit not so convincing, right? Just because this drawing didn't succeed, it doesn't mean that you cannot draw it. Okay? So we have to try to prove this. In the sense that what do planar graphs exhibit that K5 and K33 don't? That's what we will see in the rest of the class. But to even understand these things, right, we have to formalize some terminology and some concepts about planar graphs, which we'll do next. But is the idea clear? Like what we are trying to do? If that's not clear, then we will go back and see the definition of planar graphs.
Yes, ma'am, it's clear.
So now let's maybe just go back to what we saw. K4. Right? What is it that K4 had, but K5 did not have? That will tell us what planar graphs have that probably K5 does not have, and that way we can prove that K5 is non-planar. For that, we need some definitions. So what does, so given a graph G, what does a plane drawing of, so let's call this plane representation G do? It splits the plane into regions. So for example, let's look at K4. So here you have one region, this one. And then there is another region here. This one is a region. And then there is something outside all of this, this portion. So this gives us 4 regions, R1, R2, R3, R4. These regions are sometimes called faces. And this also includes an unbounded region. And this region is sometimes called the exterior region. R4 is called exterior and the other regions are interior regions. And these regions are actually bounded by a set of edges. So if you ask me what the boundary of R1 is, it's these 3 vertices and these edges. Ask me what R2 is, these 3 vertices and these edges. Similarly for R3, it is this. So exterior region also has a boundary, it's this. Is this clear? So regions are bounded by set of vertices, but usually let's say edges, we don't talk about vertices because we are talking about simple graphs, right? So edges. Is this clear what we mean by regions? So in this graph that we have colored here, the number of vertices is 4, the number of edges is 6, and the number of faces is 4. So usually books call these faces, but we can use it interchangeably. We will use faces sometimes and regions. So there is an exterior region, and there are some interior regions. So it's called, so R4 is often called the exterior face or unbounded region. Is this clear so far? So now
Yes,
let me ask some questions to ensure that You have understood this. So how many phases does a cycle have?
2.
Two. And boundary. So when I ask you what is the boundary of a particular region, you have to describe it by the set of vertices or edges. Right? That bound this region. So if I ask you what is the boundary of R1, number there. If I ask you what is the boundary of R4, the edges 1, 2, 2, 3, and 1. These bound. So some more. This has two faces, R1. We draw some more graphs that we will use later on. So there can be several plane drawings of the same graph. For example, these two. Right? A plane drawings in the same graph. So now how many, let's call this G2. How many regions does G2 have?
3.
So this is R1 of 2. So one nice thing to, so what can you say about the number of faces from these two pictures?
Very good.
So in any plane drawing, the number of faces of a given graph will be the same. It's just that the faces might be different. For example, this R1 here includes this edge, whereas here R1 does not include it. So the faces may be different, but the number of faces will always be the same in any plane drawing of a graph. And the degree of a face, so we have degree of a vertex, we have degree of a face, we have degree of a face similarly. Degree of a face is the number of edges bound. This is slightly complicated, but it's good to know. So I will give you an example and then we'll try to see all of this. So how many edges are, how many regions are there in this graph? Let me list them. So n is 12. I hope there are 14 edges. How many faces are there?
4.
So if this is not clear, like please ask questions because we are going to prove statements about planar graphs, and if this concept of face is not clear, it will get missing. The number of faces is 4. Now we have to define the degree of every face. So degree of so how is the degree defined? It's a number of edges in the boundary. But it's slight twist. So let's look at the easy ones first. So what is degree of R2?
3.
3. Degree of R4 is 5. Right? So these are easy things. Okay. So now let us look at the degree of R3 is supposed to be there. Okay. So now let's come to degree of R1. Let's start here. So this is how you compute the boundary. So you can think about it as walking along the walls. So you have 4 walls, and then there is one more wall here. So there are these things in the mazes of theme parks, right? You walk along this wall, walk along this wall, walk along this wall, and then again walk along the same wall, the other side of the wall, and then come this way. So this is what the boundary of this graph is. Right? So now what is the degree of the face R1? It's 1, 2, 3, 4, 5, 6. So 6. Is this clear?
Yes, ma'am.
Okay. So now you can also compute the degree of the outer graph, outer region. That will be 14. So I'm going to leave you to verify. Okay. So now let's, okay, so here another question. So how many faces are there in a tree?
Zero. Sorry, one.
Right, so there is just one exterior face. Okay, so now we are going to, so now this degree of a face should be like super clear.
Ma'am, I have a question. Like the degree depends upon the way we draw the graph.
Exactly, right, exactly, that's what I said. So the number of faces in the graph is the same, the plane, in any plane drawing is the same, but the faces could be different. So how do you express that in math? The degree of the face will be different. For example, here there is R1. The degree of R1 is 1, 2, 3, 4, 5. Whereas here it's only 2. That's absolutely right. So degree of R1 in G3 is different from the degree of R1 in G4. But that's the same with this also, right? Okay, so now there is something that what he said starts. So here we counted degree of this edge 2 in R1. Here also this was counted, but it was counted in R2, right? So what can you say about the sum of the degrees of the faces in any plane drawing for that? That's the next question.
They'll be the same for any diagram.
So let's count that. What is sum over?
Oh, every edge will be counted twice.
So let's say E is an edge in the graph. Yeah, that's what we are going to do. So every edge in the plane graph is either shared by two faces. So for example, if you take this edge, it's shared by R4 and R2. This, let's say this edge is shared by R1 and R2. Or it is counted twice in the same region. Is that clear to everybody? So either every edge in the plane drawing of the graph is shared by two regions, or it will be counted twice in the same region. That's not the case. For example, here, right, that's not the case. This is not shared by two regions, but it is counted twice in the same region. So now can someone fill this up?
Twice the number of edges.
Two times number of edges.
Right. Is this clear to everybody? This is important. This is really important. I hope you all understand this. That the sum of the degrees of the faces is equal to 2 times the number of edges. So this is something that is, so once, but all of this, you must remember that once you have the plane drawing of the graph, you can do all this. So now we want to understand what is it that a planar graph has. So if a graph is planar, we know that there is a plane drawing of the graph, right, that we have. Now we want to say, what can you say about, so one thing we have understood is if you sum the degree of these regions, then you will get 2 times the number of edges. So this should sort of mean why K5 was not planar. So intuitive feeling is the following, right? If you have too many edges, or in other words, if the graph is like too dense, it's very difficult to draw the graph on the plane without edge crosses. Whereas if there are fewer edges, for example, like this K5 itself, you remove the inner cycle and only the outer pentagon is there, then it's easier. Because there are few edges, it is possible or it's likely that the graph is planar. So this must sort of hint you that there must be an upper bound on the number of edges, right, in any n vertex graph that is planar. Right, if there are too many edges, it becomes messy to draw it on the plane. So now that is what we want to understand. How do we relate the number of edges? So we have three quantities here, right? Number of vertices. We have M, which is the number of edges. And we have F, which is the number of faces or regions. How can we try and relate this and see what is true for a planar? So faces are defined only when you have a plane drawing of the graph. So that you must know. So let's say G is a planar graph.
Hello, ma'am.
Hi.
Ma'am, could you just once explain how we are counting the degree of R4?
Yeah, sure. Did I mess up? It's possible. So one. So R4 is the outer region, right? Exterior. That's what you're asking.
Okay, ma'am. So the inner line that we have, that is not counted twice.
That is not counted twice, right? Because that is not in the boundary. So what is the boundary of this? Just think about this in English. What would you say as the, so let's say what is the boundary of India? Will you count Delhi in the boundary? No, right? It's interior. So it's only personal to you. So that does not belong to the neighbor. So only this portion is the boundary. So this portion is the boundary. Whatever is exterior. Yeah, this is very important. Like, please ask questions if you're not convinced. But this edge will be counted twice. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Everybody convinced? Thanks for asking the question. Actually, that's very important. Whatever is personal to you is not the boundary. You can think about this as a map.
Okay, ma'am, I understand.
Yeah,
Thank
I
you.
really hope everybody else also has understood this. So let's say G is a planar graph. It has n vertices. So when you say a planar graph, you immediately know that there is a plane drawing of this graph, right? And there is a plane representation. So once you have a plane representation of G, you have regions. You don't know how many regions are there. Let's say the regions are R1, R2, so on to RR. These are the regions. And these regions also have degrees, right? M1, M2, MR, be the degrees. So now I want to argue that, so let me just cut this. I want to bring a relationship between the number of faces and the number of edges. 3 times the number of faces is equal to 2 times the number of edges. So that's what I want to add. Is the statement clear? So I have to write the proof. So for the proof is what we will use this. So I know that G is a planar graph, and I know that there is a plane drawing of G. In that plane drawing, I know that there are regions and there are faces, there are vertices, edges, everything. So I look at all. Now I focus only on the plane drawing. Sorry.
Do we use the fact that for any region to be formed, there have to be at least 3 edges in its
So why do you think that that should be true?
should be at least.
Okay, so what she's saying is that for all I, let's write this as a plane. For all I in 1 to R, Mi should be at least 3. Is that what you're saying?
Yes, ma'am.
Okay. So let's try to see if this is true. Let's look at a region, and every region is either an interior region or an exterior region. Right? That is all that we know right now, because we cannot see the plane drawing of the graph because we don't know what the plane drawing is.
For K2, this is not true because
I will, yeah, don't worry, I will edit the statement. Say that. Yeah, sorry for this. With n greater than or equal to 3. So now I think after problems will be solved, we are going to try and see why what she said is true. But this is the statement we are trying to do. We have a planar graph with at least 3 vertices, then 3 times the number of faces, edges in the graph. So every region is either an interior region or an exterior region. So let's take that, let's say Ri is an interior region. So if it's an interior region, it should at least be like this, right? No edge forms an interior region. At least it should have a cycle. Of course, it could have a longer cycle. It could have other stuff like this inside, but at least this structure will be there. So for any interior region, Mi is at least. Now let's say that there is an exterior region. So Ri is exterior or the unbounded region. So what do we mean by this unbounded region? This shaded blue portion is the unbounded region. Now if Mi is 0, if Mi is not greater than 2, then Mi is either 0 or 1 or 2. So if Mi is 0, then what can you say? It has no edges, right? There is no such region without any edges. It has 0 edges. But that's clearly not the case. Now if Mi is 1, then what can you say? So can someone say what a region is with just one edge? Yes. A region with degree 1.
A very weird thing. Can it exist?
Interior of a loop.
Okay. What about this one? So this is a region. It's interior to this, but it has degree 1. Right? Yeah, but then this would mean that the graph is not simple. But we are going to assume that the graph is simple. So Mi equal to 1 is not possible. Let's say Mi is 2.
Then we'll have two edges joining two vertices, which is also not a simple situation.
This one, right? So only that's only possible.
Or just one edge between those two vertices because the exterior region.
Yeah, but then it means that the entire graph is just one edge, right? If there is just one more edge, then it would have had more, correct? But then we assume that there are at least 3 vertices. Let's also assume it's a connected graph. I'm so sorry, I'm putting in more details, but actually connected is not required. Is this clear? So either it's like this or the entire graph is just one edge. But we are assuming that there are at least 3 vertices in the graph. Is that okay?
Yes, ma'am.
So these cases are not possible, and this means that the degree of every region should be at least 3. So now what can we say about sum over all I and I from this thing? I know that it's 2 times n and it's at least 3 times f. So then this means that 3f is less than or equal to 2. Okay, are there any questions? Please ask questions. Okay, great. So now we have found a relationship between the number of faces and the number of edges. We didn't have anything to do with the number of vertices. So that's something I want to do. Okay, so let's look at the next connection between the number of edges, the number of vertices, and the number of faces. So this is a theorem of Euler. Let's see that G is connected. For this we need connected. Simple graph. And N, N, F are all defined. Then, so now I want to find a connection between the number of vertices, the number of edges, and the number of faces. So here, if you look at it, N is 6, N is 3. So can someone try to see if there is some sort of arithmetic connection between these? It's quite difficult, but I'm going to write it down. So the number of faces is the number of edges minus the number of. So this formula is called Euler's formula. So you must remember that. So what do we mean by this statement? So I cannot say that let G be a connected planar graph, then the number of faces is. Let G be a connected planar graph, and F be the number of faces in a plane representation of G. That's what it is. Then there is a relationship between the number of vertices, the number of edges, and the number of faces, and it's an exact equality. So let's for a minute pretend that we prove this. We will prove this. Most likely we'll finish the proof today, but let's just assume that Euler's formula is true, right? So now let's try to compare. We know that. Yes.
I have a doubt in the previous lemma. Ma'am, here if if we have a graph with 3 vertices and there's just a single edge between 2 vertices, then this is not satisfied.
Yes, yeah. So that's why it's a simple connected.
Connected. Okay.
Yeah, that is true. So what he's saying is just this, like 2 connected factors. Yeah, I wanted to rule it out. Thanks. That's good. Okay. Okay, great. So now we know this. So by Euler's formula, 3f is so this we know is less than 2n. So 6. Okay, go by the answer. Yeah. Let the n is less than 2. So what this means is any planar graph cannot have too many edges. Meaning too many, the number of edges should be at most 3n minus 6. So now can somebody figure out how to formally prove this thing? So what's the number of vertices in K5? What's the number of edges in K5? 10. Right? So you should have had at most 9 edges in order for the graph to be planar, which is actually what we were drawing, right? Except this edge, everything else we could draw on the plane without edge crossings. So what we did was, given any planar graph, if you're also given the plane representation, then you have a connection between the number of faces and the number of edges. But if the graph is not planar, you cannot see any statement like this, right? The moment f comes into picture, you know that there is a corresponding plane drawn. But this thing actually gives you a way to figure out whether the given graph is planar or not in this condition. So this implies that K5 is not planar. Now, can you do the same thing for K33?
Ma'am,
Hmm.
even though we got rid of f, the like this condition holds for planar. Acha,
Correct.
okay.
Correct. So it says that if G is a planar graph, then the number of edges can be at most 3n minus 6. And you see that in K5, this condition is not true. So K5 is not planar. Correct?
Yes, ma'am.
If it had one edge less, it would have been planar, clearly, because we also drew the same thing without only one edge we were not able to draw without edge crossings. Everything else was fine. So this gives you a way to check whether the given graph is planar or not. But unfortunately for K33, what happens is this condition is satisfied. So only when this condition is not satisfied, you can say that the given graph is non-planar. Right? So K33, if you look at it, the number of vertices is 6 and the number of edges is 9. So that it satisfies this criteria. But yeah, I want to say that it's non-planar, at least because we were not able to draw it. So now I will give a short exercise. Yeah, this is not difficult, so I'm going to do this as an exercise. So if G is a connected planar simple graph with n vertices, n let's say is greater than equal to 3, and no cycles of length 3, then the number of edges is increased. Okay, so please try this exercise. And this corollary of this, you get that K33 is not. So these two will be an exercise. So now we have formally proved that K5 is non-planar and K33 is non-planar, assuming that you will do the exercise. So now okay, maybe I can take 2 3 minutes extra. Let's do it. So, so what do we want to do this statement? Right? This is the statement. So I know that G is a planar graph. So there must be a plane representation of G. Consider. So you have a drawing. So this means that you have a drawing of G in your hand where no edges cross. So now what I want to do is I want to slowly construct this graph one edge at a time, whatever plane drawing you have in your hand. I'm going to draw the same graph by adding one edge at a time and then see how the number of faces increase, right? The number of edges increase by 1. But how many faces can we introduce at every stage? Right? So initially, the graph is empty. Now I'm going to start drawing G. So I add one edge. A1. So now the number of vertices is 2. This is 1. And how many regions are there? So let's call this N1, M1, R1. Or yeah, I think so. How many regions are there?
One.
One, right? There's just one exterior region, it's capital R. So now I'm going to add. So let's assume that we are in the kth stage. Okay? So I've added like some number of edges. At every stage, I'm going to add one edge. Now I'm going to add one edge to get. Then I want to complete the graph. Right? In the end, after all the edges are added, end stages, the entire graph will be there with you. A plain drawing of the graph will be there with you. But now you are in, let's say, you have completed k stages. Let's say completed k stages. So you've added k edges, and you are now in k plus 1 stage. So at this point, you already have a graph in your hand, right? Some plain drawing. And in this drawing, there will not be any edge crossings. There will be stuff here, something like this. There will be more stuff here. We don't know what these are. There will be k edges. Now, this for convenience. Now I'm going to add the k plus 1 edge. So what are the possible cases? So when I add an edge, I select an edge from the drawing and I say, okay, this I'm going to draw. So let's call this GK, right? The drawing that we have at the end of the kth stage, completed k stages, and we have a drawing GK. Right? Now the goal is to construct GK plus 1 from GK. Is this clear? Is the goal clear? If there are
What's the stage?
right. So I'll pick one edge. Let us say I know that the graph is planar, right? So I know that there is a plane drawing of the graph on. So there's a drawing of the graph on the plane without any edge crossings. What I'm going to do is I'm going to recreate the same picture. Let's say that you have the picture and I don't know the picture. So I'm going to try and recreate the picture that you have by adding one edge at a time. So at the end of at the end of step K, let's say kth step, I would have added k edges. Now I have to take one more edge and draw that one edge. So I look at the edges in the graph and I say, okay, now I'm going to draw this edge. Now I have to draw this edge such that there are no edge crossings. Right? That's my goal. So it means that I am going to sample one edge at a time from the OC graph. I'm going to try and draw this. So now at this point, first I had an empty sheet in my hand. So I sampled one edge, A1, B1, and I drew that. And I realized that Euler's formula is satisfied for this base case. There are two vertices, one edge and one region, and it's fine. So now I have to add the second stage. I will add one more edge. Even then, the number of regions will be one. The number of edges will be there. The number of vertices will be there, and I will see that this condition is satisfied. At the third stage, I will add the next thing. When I add the next thing, the number of vertices will be same. Number of edges will increase, but now the number of regions will also increase. Now there is an interior region. There is an exterior region. So this is what we are going to try and do. So this way, let us assume that inductive is completed like k stages. K steps are over. Now I'm in the k plus 1 stage. So I already have one plane drawing in my hand. I have to add one more edge. Right? So one possibility is that, is this clear to everybody? If it's not clear, we'll do this again slowly. No hurry.
Ma'am, should we also add vertices along with edges?
Right. Yeah. So we will see that. So let's say that this AK plus 1, BK plus 1, right? This edge I want to add to the drawing that I already have. So one case is that either, like what he said, both the vertices are already there in my graph. Right? AK plus 1 is also there and BK plus 1 is also there. Or it is also possible that one of these vertices are not there. Right? Let's first assume that both the vertices are already there, only edge are going to draw. So now, what can you say about AK plus 1 and BK plus 1? So now we are going to assume that AK plus 1, BK plus 1 are already.
Ma'am, could it happen that neither of them are in the graph already?
So we are assuming it's a connected graph, right? So one of them will already be there in the graph. We are going to construct the drawing in such a way that we are going to like only expand edges. So one of them will be there. because the graph is connected. If the graph is not connected, you cannot do this. Is that clear?
Yes, ma'am.
So let's assume for now, let's take the both the edges are both the vertices are there on the edge of that. Right? Now, what can you say about these two vertices? Can it be that one vertex is in R1 and the other vertex is in R2? Can this happen? This is R1, this is R2, and we have two vertices like this. Let me draw this in a different color so I can delete it later. Is this possible? So this is like one region, R1. And let's say your AK plus 1 is here. R2, BK plus 1 is this. If this is the case, right, then it should be clear that you are going to have an edge crossing. Because this region also has a boundary. This region also has a boundary. So then if you add this edge at this stage, then there must be an edge crossing.
But ma'am, what if the vertex is not hanging in the sense?
This way.
Yeah, but like, what if it is like AK plus 1 that you have drawn in the purple graph in the GK?
You mean this way? You mean this way, right? This is AK plus 1, this is BK plus 1.
Yes, ma'am.
Okay. So what can you say? Like what she said. That is what it's
What if there is no clear region in which the vertex?
Then you can add, right? Then you can add the edge without edge crossing.
Yes, probably.
Is that not clear? Okay, so what are we doing? So first, the base case is clear, and we are in the case stage. And the case stage, we have a plain drawing of the graph. You have added k edges. Right? So the number of vertices is nk in the graph. So I will just delete this. So we have a drawing at the end of case stages. The number of vertices is nk, the number of edges is nk, and the number of regions is r. And let's say so far we have satisfied this condition. So the number of regions is the number of vertices edges plus 2. So far it is true. Now you are in step k plus 1. So this is like an induction. Right? We are going to assume that this is true so far. And now we want to add one edge to GK to produce GK plus 1. So in step K plus 1, we add an edge. Just one edge to GK to get GK plus 1. And let's say that that edge is AK plus 1, BK plus 1. For now, in the first condition, we are going to assume that these two vertices are already in the graph GK. So then, if you look at it, what Aditi said that can happen. But then what can only happen is that these two vertices AK plus 1 and BK plus 1 must be on the boundary of a common region. So both of them should have a common region like this one. It is quite possible that this happens. For example, this is your BK plus 1. It's, yeah. Then you have to add this edge. That is possible. But what we are trying to say is that it should be on the boundary of a common region. Both of them should belong on, there should be one region in whose boundary AK plus 1 and BK plus 1 should be there. So there must be common region is boundary both AK plus 1 and BK plus 1. Okay, So now, suppose this is not true, right? Suppose like what I said, something weird happened. And there is you'll have to sort of cross the edge only. That's the only way, right? Cross two edges to draw the graph. If that is the case, then whatever drawing you had, right, is not a plain drawing of the graph. Okay, so let's just go back and see only this case, and then maybe the remaining let's do next time. So we're going to start with a planar graph. Because the graph is planar, I know that there is a plane representation. Insert space in this. Just cut this. So one thing I know is that this graph is planar and there is a plane drawing of this graph. And let's say that one of you hold the plane drawing of the graph and I don't know what the plane drawing is. My only goal is to try and create a plane drawing of this graph where this condition is satisfied. So I know that G is a planar graph and there is a plane representation, which means that you have a drawing. So what does it mean? Initially with just one edge, there is G1, and then I can extend G1 to another graph G2, where I add edges E1, E2. I can extend it to G3 by adding E1, E2, E3, and so on. Right? This way, I can replicate the graph that you have. Is this clear so far? Even if it's just K4, let's take K4. This is my E1, E2, E3, E4, E5. So G1, my first subgraph is just this thing. The second subgraph, let's take this is G2. This is G2. And G4 is this whole graph. In G5, I add this. So this way, I can progressively create this original graph G in stages. So there is GK, GK plus 1, and so on. Right? In GM minus 1 or how many ever edges are there, in the last phase, the entire drawing I have and you have will be similar.
Yes, ma'am.
Right. So first, in the base case, you pick some arbitrary edge. And you add this edge to the original graph. There is nothing empty initially. In the initial stage, it's empty. So there's only one edge. You add that edge and this Euler's condition is satisfied. Now I have to ensure that at every stage I can add edges and Euler's condition will be satisfied. Okay. So let's just finish up this case alone and the remaining cases we can do it next time. So now we are in kth stage. So I have added k edges and let us assume inductively in the kth stage this condition is satisfied. So the number of regions in the kth stage is equal to the number of edges in the kth stage minus the number of vertices in the kth stage plus 2. Now you are in the k plus 1th stage. Right? So you have to add one edge to the graph gk to get the graph gk plus 1. And let's say the edge you are going to add is ak plus 1, bk plus 1. Like someone had asked, it is not necessary that these vertices are already in the original graph. But as a first case, let us assume that both these are already in the graph. So case 1 is both ak plus 1 and bk plus 1 are already in the graph gk. Right? So from gk to gk plus 1, you are just adding an edge. No vertex addition is happening. So now, if these two vertices are not on the boundary of any common region, you cannot add ak plus 1, this edge, to the graph gk to get a planar graph. But I know that all of these are planar because you have a plane drawing of the graph. Right? So there is a sequence of in which you can add edges and reproduce the drawing. Right? So the only case is that either it's like this is a possibility. It might be like this, the same thing. And let's say this is your ak plus 1 and This is your bk plus 1. bk plus 1. Let's say this was the original graph. Okay? So either this way you're going to add or this way. So just have particularly there. Okay. So yeah, we have to complete the proof, but I presume that at least base case is clear. We will see this, see the details next time. And at least what is expected is you understand what planar graphs are, what is number of edges, number of vertices, number of faces. Euler's theorem, maybe we'll do it slightly more slowly next time. But at least until base case, it should be clear. We will redo Euler's theorem. And please try this exercise. Okay, so as an aside, so what we will see next time, I just want to mention. So we will finish the proof of Euler's theorem. We'll do some coloring statement. And one thing to think about is now we have formally proved that K5 and K33 are both non-planar. So now one might question that can K6 be planar? Is it possible? Do you think that K6 can be planar?
No.
K5 is not, right? And K5 sits inside K6. So K6 is also not planar. K7 is also not planar, and so on. So Kn is not planar for any n greater than or equal to 5. Similarly, K33 should also not sit inside any planar graph. Right? So what it means to sit inside, we have to define. But this is also a very well-known theorem. Says that in some sense, any planar graph cannot contain within itself a copy of K5 or K33. Right? We have to like formally define what contained within the graph. But we will do that. And some more concepts maybe in the next lecture. So it's good if you understand until the base case of Euler's theorem for now, and then we prove the rest again. We just messed up this. But I hope like at least the definition of planarity is clear. If there are any questions, I'll just stop the recording.
Recording stopped.
Are there any questions? Yeah, I will try to make this proof of Euler's theorem more illustrative next time. Yeah, maybe should give some examples. Yeah, I'll do that next time. So if there are any questions, then we can take. Otherwise, let's look next time.
Maybe the second diagram.
This one.
The second one.
This
Yes,
one.
that one.
Uh,
Shouldn't bk plus 1 be connected by one edge to the cycle?
right. So you mean that it should be this already?
Yes, ma'am, because we're taking the first case where all the vertices are already in the.
Yes, yeah. So what I was about to say, at least in this picture, is maybe I didn't convey that so if we can assume that one of AK plus 1 or BK plus 1 is already in the graph, because we're going to assume connected planar graphs. So if both of them are already in the graph, then what you said is true. Either it will be this way, or if one of them is not in the graph, you have to add the edge, then this particular edge wouldn't be there. So what we want to intuitively understand is if the vertex is already in the graph, then by adding this edge, right, I will increase the number of regions by 1. So I've now added a region. So whatever was initially R1 will now become R11, R12. But if I add BK plus 1 itself to the graph, maybe this edge wasn't there, say, then by adding this edge, I won't increase the number of regions. Yeah, so that is what I wanted to say. Probably that's why this picture is there. But what you said is right. For the first case, this will be there. So when both,
No, ma'am.
so the intuitive thing is that when both the vertices are already in the graph, if you add this edge, you will only increase the number of regions. So then you added the number of edges by 1, but the number of regions also increased by 1. So this equality was still true. Or what can happen is you just added this vertex, right? That is fine. But in that case, the number of regions won't increase. So we have to see that how you maintain this equality in that case.
Then the number of edges and the number of vertices both will increase by 1, right? So,
right. So nk will become nk plus 1 and nk will become nk plus 1. Right?
yes, ma'am.
Yeah. So those cases we have to handle. That's what I was about to say. But you're right. At least in this case that we are seeing, you have to draw this edge. I mean, there are no dangling around.
Ma'am, can we write the proof like without drawing pictures?
It is not. So you're saying that you don't want to do a constructive proof, right?
I mean, like without drawing, just using formula argument. How do we prove this?
No, actually, I haven't. So maybe I will try to figure it out.
Okay.
Yeah, maybe you can do an induction. I think that is possible. Yeah, but then one possibility is you may have to use the other inequalities or inequalities that we saw earlier. That is possible, like the relationship between the number of faces and the number of.
Ma'am, like in the like why we are drawing pictures, like is that I mean the reason why we are drawing pictures is because like we can't define regions. Like how do we define spaces without?
Yes, that's what I'm saying. So if I have to get into this an equality that uses spaces, then it means that there is an underlying picture that I have, right? The concept of faces comes in only when I have a drawing in my mind.
Yeah.
So without a drawing, I don't know how to talk about faces.
Oh, okay, ma'am.
So that is one reason why we are going for drawings. But maybe it is possible to do an inductive argument.
Okay,
yeah, I will try to see this.
Oh, thank you.
Because we are not actually interested in what the face is, right? We are only interested in number of faces. So it is still possible that we can do it without the drawing.
Okay, ma'am.
So if I find an easier proof, then maybe I will just skip this whole thing and